Hi, hi. Welcome to this video on ISP Task 2 in Particle Physics, Unit 4 of Edexcel Physics on the Move. So last time we looked at Rutherford scattering. This time we're moving on to particle accelerators and bubble chambers and how they work. So remember, if you're really trying to push for an A and A star, you've got to have a look at how magnetic fields and electric fields can be used to produce circular motion. So let's go straight into explaining everything tasks. So I've been a bit cheeky with this one because this is pulled literally straight out of an exam question, which is actually included in the ISP. So it's talking about the role of electromagnetic fields in particle accelerators and detectors. So I won't go through this here, but I definitely will go through it when we go through the exam question that is on this. So don't worry about, if you've written loads of notes for this bit, great, because it will only help you in that exam question. But if you're struggling with this, wait until I go for the exam question, and that will help you out to write a decent answer for this area. Remember, there's a few diagrams you can include for this as well. Right, so let's get stuck into task 2 questions. There we go. So we've got a picture here. And let's talk about the production of radioisotopes in cyclotrons. Okay, so what the first thing they want us to do is they want us to figure out the speed of the protons. They want us to show that it's about 10% the speed of the light. Okay, so they want us to figure out the velocity that these are travelling at, essentially. Okay, so we've been given some information. We've been given information on the magnetic field strength. We've been given some information on the radius. Okay. And we know it's a proton, so we know its mass, and therefore we know its charge as well. So we want an equation really that's got all those variables in there. And if you look at your equation list, the only equation that's going to have is this one over here that ties together everything that we've discussed. Now, what I say the biggest thing about this equation is this is, whenever you think about circular motion, cyclotrons, this is the equation you lean on. Okay. This equation is the one you think of whenever you've got anything to do with circular particles moving in circles because of a magnetic field. So this is the equation you go straight for. Let's just zoom in slightly so we can make that clear. So make that clear, and then it gives that focus. Let's try and get a bit more focus. There we go. Well, let me just clean the camera a bit. That's just made it worse. That's partly because I'm writing in green as well, which I know it doesn't like. There we go. Okay, so remember radius, mass, velocity, magnetic field strength, charge. Okay, so we've rearranged for V. Okay, so V is going to be equal to BQR over M. Okay, and then it literally is just putting our values in for that. Okay, so as soon as you put your values in, you should end up with something about 2.9 times 10 to the 7, which is pretty close to, which is pretty much 10% the speed of light. I'll just double check that on my calculator, and then I'll put it underneath the camera so you can see it. So BQM, so B is going to be 200 times 10 to the minus 3, Q is going to be 1.6 times 10 to the minus 19, and M is 1.67 times 10 to the minus... So is it 27? Yeah, bracketed all that up. Oh, I put M in the wrong place, have I? Yeah, I have. Right, it was supposed to be times by 1.5. M is going to be the divide. Let's just do that again. 200 times 10 to the minus 3 times 1.67. Sorry, 1.6 something minus 19 times by this radius of 1.5 meters, and then we'll divide that value by 1.67 to the minus 27. Yeah, so you can see the value we end up over there is 2.9 times 10 to the minus, times 10 to the 7. So that's 10% of the speed of light. Nice question to warm us up. Should have made this webcam bigger so you can see everything. I'll bring it up here as well. Okay, so nice question to warm us up. Only worth only worth 3 marks though, but still a nice 3-mark question to get us started. Okay, calculate the approximate time taken for the proton to complete the last semicircle of its orbit. Okay, so what they're actually asking us to figure out here is the time period. Okay, so essentially the time period is one of the frequencies, so we need to use the frequency to actually allow us to do this. Well, what equation can we actually use to allow us to do that, considering they haven't given us any information on that? So let me show you where you get that information from. Actually, I tell you what, I'll show you on the mark scheme rather than... There we go. I've gone past it on the mark scheme, so I'll see if they've got it here. Right, no, well, they haven't got it as clearly. Well, they've got information here in terms of angular velocity if you had it. But the idea is, if it's going in this idea of circular motion, that distance it's going to travel, okay, is the circumference halved. The circumference is 2 pi r, okay, so half the circumference is going to be pi r. So for the last semicircle, the distance is pi r. Okay, the speed it's going at, well, we've just figured out that value. Okay, so that will tell us the time. So that distance, pi times r, divided that velocity, will give us the time it takes to go around that distance. Okay, so I'll show you that in the mark scheme. There we go. Okay, there are 2 values that we actually had. So time taken for that final half semicircle. Hence, calculate the frequency of the accelerating PD. Well, frequency is whatever time period, but that's the time only for the last semicircle. Yes, that's the last semicircle. So that's the frequency. The frequency is 1 over the time period. Okay, so we're 1 over the entire time period to allow us to figure out the frequency. Okay, so remember that's just for a semicircle, so that's going to be for the entire time period. Okay, 6. So this is all I said I was going to go for in a bit of detail. There's up to 10 scoring points on this. Okay, so remember this goes back to the explaining everything task as well. So they're asking for the role of magnetic fields in particle accelerators and detectors. Okay, so the only thing that isn't mentioned here is electric fields, but I'll go through electric fields so you can add that to your explaining everything task if you need to. So let's talk about magnetic fields first and accelerators. So they change direction and motion, so in other words, they put objects into circular motion. They apply a force that's perpendicular to the motion of the particle. Okay, so that's the idea of Fleming's left-hand rule in there. So they essentially put these particles into circular motion. So if they're putting a particle into circular motion, they must be applying a force. So the size of that force is equal to BQV, that we know from the electric fields part of the course, but that's also equal to mv squared over r, because it's putting it into circular motion. Remember the cyclotron in class, we've derived the equation. This is also in your textbook as well, which shows how the time period is related to this. Okay, so that shows that the frequency of the time period is not dependent upon the velocity of the actual particle, just the sorry, 1 second, I'm just going to bring something back a bit. Yeah, just the mass, and sorry, the mass, the charge, and the magnetic field strength. So this is why the magnetic field strength is so important. If we get the magnetic field strength right, our life becomes a lot easier. So to quickly mention electric fields. Okay, electric fields, remember, are used to accelerate in terms of velocity. Magnetic fields are used to accelerate in terms of direction, while magnetic fields are used to accelerate in terms of direction. Electric fields are used to accelerate in terms of velocity. Right, I just lost something in front of me. I'm just going to get it back. Here we go. Right. So remember, it's a fixed frequency or fixed voltage required for acceleration, which sort of ties in with this idea. Synchrotrons don't have that; they vary. Okay, because they sync up essentially. But it's a fixed voltage that's usually required for acceleration. Remember the idea of the fact that we've got 2 Ds. Okay, so if you want to sort of draw those Ds in, okay, so remember there's 2 semicircular Ds with the electric field between them and the magnetic field through them. So the magnetic field is going to be acting through electric field between them. Remember, synchrotrons have this idea of a fixed radius, and they vary the magnetic field strength to vary the time period and therefore get the frequency right. So in detectors, the magnetic field allows us to detect the charge of the particles, and also the momentum and the speed and the energy and the mass. And that's all from the idea of the equation that was stated before. Okay, because what actually happens is the charged particles go into a curved path because of the fact they're in a magnetic field. Okay, so remember, electric fields can be used in detectors again just to figure out the charge because they're pulled over to one side or the other. It'll also figure out whether something's more massive than something else because the fact it gets pulled over quicker or slower because of the idea of momentum. So we've got a student investigating CERN, and they're given a bit of information about CERN. The fact the tunnel is 8 kilometers in diameter, and the fully accelerated particles circle the tube 20,000 times in 1 second. So that's 20,000 hertz. Okay, essentially, is the frequency, or isn't the amount of times it goes around. 20,000 times in 1 second. That's crazy, crazily large amount. So, calculate the speed of the particles and comment on the likely accuracy of this statement. So we want to figure out what the speed these particles are going at is, and therefore whether this statement's accurate or not. So speed is equal to distance over time. Okay, so here's the idea of, or velocity is equal to, let's go with speed because it's linear speed they're actually after, is equal to distance over time. So the distance is the idea of the circumference, that's pi d, and the time it takes place, well, we don't have time yet, okay, but we can figure that out from the fact that in 1 second it's going to go around 20,000 times. So if I multiply this top number by 20,000 and did this as 1 for 1 second, that gives me the distance it does in 1 second, and therefore I can figure out the speed. When you do that, you should end up with a value of about 5 times 10 to the 8, which is ludicrous because it's faster than the speed of light. Okay, so a nice question to be given in an exam paper. You can already tell when they say calculate on the likely accuracy statement that some things could be wrong. Okay, so it's going way too fast is the issue. Right, question 8. Straight away when we see that, we should identify that as an electron gun. That's from a cathode ray oscilloscope. So we've been given the electron voltage. Okay, so in other words, we know the voltage has been accelerated by. So remember, as soon as you give me the electron voltage, you can figure out speed. And it literally is from the idea that EV is equal to half mv squared. So all of the electron voltage is converted into kinetic energy. So EV is equal to half mv squared. That's the calculation that you need to do. So it's a 3-mark calculation. So it's a pretty straightforward calculation for 3 marks. Remember, you need to rearrange that for V afterwards. So you should end up with something in the region of about 2 times 10 to the 7. So what is phosphor coating, which produces green light? Each photon has an energy of 2.4 electron volts. The efficiency of the conversion of the electron's kinetic energy to light in the phosphor is 8%. So only 8% of this 1.2 kilo electron volts ends up becoming light. Calculate the number of photons that will be liberated by the arrival of 1 electron in the beam. Well, each one of these electrons is going to have this 1.2 kilo electron volts. Okay, but remember, only 8% of that is going to get across to the phosphor. So essentially, it's to 1,200. That's 1.2 kilo electron volts. Okay, I need to multiply about 0.08. Okay, because that's telling you it's telling you essentially the percentage. Okay, it's telling you what percent is now actually going to get across. Okay, so only 96 electron volts. Let me show it to you on the calculator. Only 96 electron volts are delivered actually to the phosphor. Well, each of these is 2.4. So now we need to do 2.4 divided by, so 96 divided by 2.4. So it tells you how many of these electrons must actually be in there. 96 divided by 2.4, so that gives you 40. 96 divided by 2.4 gives us 40. So 40 electrons must be released, or 40 photons, sorry, must be released. Okay, 40 photons must be released. B. In a badly designed cathode ray tube, electrons arriving at the screen are not conducted away but built up in an area where the beam hits. That is not good at all. It's not going to produce any decent image. Explain how this would have an adverse effect on the amount of light emitted by the phosphor. You may be awarded a mark for a clarity of your answer. Okay, so remember, if the electrons all build up in one area, you have a large amount of negative charge in one area. So they all end up repelling other electrons. So those electrons that build up apply force on the electrons that are trying to get there. So it works in a similar way to capacitor, you know, so it's going to be harder to get across to it. That's why it's harder to charge a capacitor when it's getting close to full charge. So it's harder for other electrons to actually come across and hit the screen because in fact the electrons are built up. So in other words, the electrons are decelerated and work is done by these electrons against motion, essentially, which is not good. So that means they have less kinetic energy. If they have less kinetic energy, it means they're not going to release as many photons from the calculation that we had before. So not so many photons will be released. Okay, so what that means essentially is in this oscilloscope the trace will not be so bright. Okay, so that's the end of ISP Task 2 in particle physics. So that ties up everything up to particle accelerators. Okay, so what we've got coming up next time is some work on fundamental particles and the ideas of E equals HF and how it's linked with E equals mc squared. E equals HF, remember, is from AS, and E equals mc squared. This is your first real introduction to that. Okay, thank you very much for watching, guys.